Okay, so for today, as you can see, we're going to be solving systems that contain three variables, and that means they're going to have three equations. And we're going to have two different methods to utilize. We're going to start with an example of elimination using solving for three variables. So what we're going to do first in this process is I would always recommend that you kind of overlook this whole system and see if you can start picking out a particular variable, either x, y, or z, that looks like it would be the easiest to eliminate. What do you think there, Dalton?
The y.
I would agree with that. The y variable would eliminate if I added these two together. They would cancel. And that would also be true if I took this first equation and combined it with the last equation. Okay? So what I'm going to do, as you can see there in step one, is I'm going to make two pairs. Now obviously if I'm going to come up with two pairs with these three equations, then one of these equations will have to be used twice. It'll be used in each pair. So just for sake of illustration, I'm going to number these equations. Equation 1, 2, and 3. Not really necessary to solve, but just so you can track with me. So what I'm going to do, as step 1 says, is I am going to make a pair using equation 1 with equation 2. So I'm just going to write 2x plus y minus z is equal to 5. And then I'm going to partner that up with equation 2, 3x minus y plus 2z is equal to negative 1. Okay, so that's one pair of equations. And now, just like we said earlier, it makes sense to pair up 1 and 3 because we can also eliminate y there. So 2x plus y minus z is 5. That's equation 1, partnered up with equation 3, x minus y minus z is 0. Okay, so here's the deal. We've come up with the two pairs that step 1 is talking about, and now step 2 is very important because we need to make sure that we eliminate the same variable within each pair. Okay, so we kind of figured that out ahead of time. We did a little planning. We said y would probably be the best. So just as a reminder, whatever variable you decide to eliminate with this pair, you must also eliminate that same variable over here. Okay, doesn't matter which variable it is, but whatever you decide on, make sure you eliminate the same within both pairs. Okay, maybe somebody just read those off to me so I don't have to go back. What's that first equation there? The first pair?
2x plus y minus z equals 5.
And below that?
3x minus y plus 2z equals negative 1.
Okay. And then we'll get somebody else. Avery, what about the other pair? What was it?
2x plus y.
Same one.
Minus z.
And below that?
X minus y minus z equals 0.
Okay. So now we're going to go through the elimination process with each. We're eliminating y in both cases, and that's going to take addition, of course. So when I add like terms all the way across, just like typical elimination, I get 5x, y is canceled, negative 1 plus 2 is plus 1z, and then over here I get 4. Okay? Do the same thing over here. It will also take addition to eliminate y with this pair. So let's add all the way across. 3x, the y is eliminated. Negative 1 plus negative 1 is negative 2z, and that equals 5. Okay? Well, you can probably guess what we're going to do now. Anybody want to guess? Go ahead, Riley. Exactly. Now we're back to familiar territory. We're back to two variables with two equations. So we'll just go ahead and put that down with step number 3. 5x plus z equals 4. And below that, we'll put 3x minus 2z equals 5. And let me see, Abigail, what do you think, which variable, either x or z, would be the easiest to eliminate? And how would you do that? I agree. She said z. What would be the way to go about eliminating z? Yeah. Top equation by 2. Nothing done to the bottom equation. She's exactly right. So multiplying by 2 across the top, we get 10x plus 2z is equal to 8. And I'm not doing anything to the bottom equation. And we can eliminate z with addition. So we get 13x is equal to 13. So we got our first variable solved for. There's 3 total. We know what x is. Now at this point, as you can see in step number 4, we're basically, you could think of it as backtracking through what we've done. Because once I found this first variable, I only know what one variable solution is. Now I'm going to go back to where there are 2 variables, and I can pick either equation to use. So Keegan, it looks like we're going to be solving for which variable next? Well, we know what x is. X is 1. So based on what you see there in the blue, we're going to find z. Exactly. So that's why I'm saying we kind of backtrack through our work. Let's take this result for x and plug into either one of those. It doesn't matter which. All right. Keegan, do you have a choice? Do you have a preference? Top one? Okay. Let's let x become 1 in the top. 5 times 1 plus z is equal to 4. So hopefully you can see that z is equal to negative 1. So we're 2/3 there to our answer. We got 2 variables. Now we just need to find y. So at this point, after you found 2 of the variables and you're looking for the third and final variable, now you're going to go all the way back to the beginning. And you're going to go to one of those original 3. And you pick. It doesn't matter which. Pick the one that looks like it might be the easiest to work with. Let x be 1. Let z be negative 1, and then you can find y. Okay, so I'm going to do that. I'm going to go all the way back. And let's see, Meredith, which one do you think? Equation 3, okay. We said x is 1. We're solving for y, and we said z is negative 1. Is that right? Okay. It should be the last one. Yeah, we're here. We are at the point now where we have 2 variables, and we're going to go all the way back to the beginning. And really doesn't matter which one you pick. Meredith picked the last one. I probably would have too. So here we go. So 1 plus 1 is 2. When you solve for y, you get negative y is negative 2. So positive y is positive 2. So for these systems in 3 variables, we don't have an ordered pair, we have an ordered triple. And so our answer is going to be written like this. X is 1, y is 2, z is negative 1. And we're done. That wasn't too bad, was it? It's just a little bit more involved than normal 2 variable elimination. So my word of advice is be careful. There's a little bit more work involved. One little mistake throws the whole thing off. So make sure that you're cautious and careful and neat with your work. Yeah, question?
Can you graph those? I'm not trying to make it complicated, but is there a way to graph those?
There is. We're not going to, but this is actually 3D. Okay, that's actually a great question. For our purpose in this class, we're going to solve word problems where we're trying to find 3 unknowns. But this actually shows up in real life, and there is a 3D coordinate plane. All right, so what I want you to do is I've given you a 3-variable system there. That's you see the slide that's labeled "You Try," and I've already given you the answer to shoot for. I want to see if you can do this on your own using the elimination method. So let me just kind of set you up in case you forgot. You're trying to see if there's a variable right off the bat that would be the easiest to eliminate. And then you come up with your 2 pairs. Okay, one equation, of course, is going to have to be used in each pair. And then you want to eliminate that same variable within each pair. That's key. Yes? Yeah, I know. I told you that. That's what I want you to shoot for. Okay. I know you're doing this on your own, and there's a bunch of different ways you can go about this. You can pair them up in, well, several different ways. You can try to eliminate any variable you want at the outset. But something interesting will happen for some of you, and it looks like it's already happened. So I want to go ahead and address that. I think it's happened here, okay? All right, so here's what we're doing. It sounds like, or it looks like, you wanted to eliminate Z, which is probably what I would have done. And you paired up the first 2 and then 1 and 3, correct? Okay. So let me see if I can just get there without writing all this out. When you pair one of them up, you get this equation. And when you do the other 2 as a pair and eliminate Z, you get, what is that? Okay, so what happened here is great. This is awesome. You ever hear kill 2 birds with 1 stone? Sorry. Well, that's what happened here. In the process of trying to eliminate Z, we also eliminated Y, which is awesome because we found our first variable value, which we knew that was 3. Well, to find Y, it kind of saves us a step. All we have to do now is go over here to this other equation and plug X in for 3 in for X, and we'll get Y. So whenever 2 variables eliminate with 1 step, all you have to do is take that value and plug it into the other equation. And that should be pretty easy to find out what Y is. Does that make sense? Doesn't always happen that way, but when it does, and this is a little bit different than our previous problem, so I wanted you to be aware. Any questions? Okay, so it looks like everybody had success. We're doing good with the elimination method. Now let's take a look at how substitution is a little bit different. It's very similar. As a matter of fact, there is going to come a point in substitution where we're going to go back to elimination, but it starts off with pure substitution. So remember back when we were doing substitution with 2 equations, 2 variables, we said that we need to pick a variable to solve for, and in general, if we can, we want to pick a variable that has a coefficient of positive 1. Those are always the easiest to solve for. Well, in this system, we have 3 good choices, 3 best choices, really. None of them are really better than the other. We could solve for X in this first equation. That would be easy. We could solve for Z, just as easy, in the first equation. Or we could solve for Y in the bottom equation. Any of those would be equally as easy as the other. Well, here's the deal with substitution. You pick a variable, solve for it, and then you replace that variable in the other 2 equations. We're used to replacing just in the other equation. Well, now we have to replace in the other 2. So on your notes, I've provided you with an example. First of all, I solved the top equation for Z. So just in case you're wondering, well, how did you solve for Z? I subtracted X from both sides. I added 3Y to both sides. Negative X plus 3Y. There's already a positive 6 on the right side. Okay, and just to save you a little bit of time, your next slide shows how this expression replaced z in the other two equations. Do you see that? Here it is pictured for you. So all I'm showing here is equations 2 and 3 because those are the two that had to have z replaced. And the blue is actually what we came up with for z. So at this point, it's really just almost like Algebra 1. We need to get rid of the parentheses with the distributive property, and then we need to combine like terms. All right? So let's run through that real fast. I'm really distributing -1 here to this group in blue. So that's going to give us 2x minus 5y plus x minus 3y minus 6 equals -2. Okay, so I've got rid of the grouping symbols with the distributive property, and now I'm going to combine like terms. 2 plus 1x is 3x. -5 minus 3y is -8y. Now constants need to go on the right side. So I need to add 6 to both sides, and that's going to give me 4. Okay, now the same thing has to happen down here. I call this this is cleanup. Distribute the 2 to all three of these blue terms. So -x plus y, and that's going to be -2x plus 6y plus 12 is equal to 7. Combine like terms. -3x plus 7y, and now this constant needs to be moved, and it's going to be done with subtraction. So hopefully you can see how this right side is going to be 7 minus 12, which is -5. Okay, so is anybody not with me so far? Everybody's good? Well, now, question. Yeah.
How do you choose the numbers from over here to get on that?
Let me see if I understand your. How did I choose 2 and 3? Is that what you're asking? Well, let me just ask this. We're here with these two equations. Well, now we're back to elimination. So it starts off substitution, but when you get down to this point, you're back to setting up elimination, like we did before. So 3x minus 8y is 4. And -3x plus 7y is -5. And this is setting up for us perfectly for elimination because we don't have to multiply by anything. All we're going to do is add. And when we add straight across, we get -y is equal to -1, so positive y is positive 1. Now at this point, we're back to what we were doing before. Matthew, which variable will we find next? Okay, we'll find x immediately next, and how? How will we find x as our next variable? Yeah?
We'll plug the y back in and then the original.
Exactly. So we'll go back to one of these, doesn't matter which, and replace y with 1 and solve for x. And then how do we get our final variable, which is z? How's that going to happen? Back into, all the way back to the beginning, the original 3, and you get to pick. It really doesn't matter which. So let's see, has anybody already done that? You got a final, Riley, what'd you get?
4, 1, 5.
Okay. Who else got that? Maybe you're still working on it. Okay, that's fine. And that should be your answer for the ordered triple. So my last example for this video is actually just setting up one of your homework problems, one of the word problems. There's only 2 on this assignment. So what I've done here is I've just typed out the scenario for number 18, And I wanted to use this as a way of maybe helping you come up with the system of equations represented by this paragraph. All right, so it's going to take a little bit of practice, but I think eventually as you do these more and more, you're going to be able to take sentences and phrases and come up with equations that those sentences and phrases represent. So we have this, just to kind of give you an idea, we have this swim meet, and there are first, second, and third places being awarded. There are 24 people that actually placed either first, second, or third. There are a certain number of points awarded for first, second, and third, and all the points added up for all the participants that placed, total 53. And then we have this last sentence here that talks about the fact that there were as many first place finishers as there were second and third combined. So let's just kind of work our way through this. Here's a clue, I think, as far as the type of equation that needs to be written. The fact that there are a total of 24 individuals placed. Okay? And then here's something else that we need to take note of. What is it that the problem is actually asking us for? They want us to write a system of 3 equations that represents how many people finished in each place. Well, whatever the answer to the problem is will determine how we set our variables up. So I got 3 variables because there are 3 different ways people could finish. So I'm going to let x be the number of people finishing first. Okay, that's partly what we're asked for. How many people finished in each place? So I need a variable to represent each place and the number of people that finished. Number of people finishing second will be y. I'll just abbreviate a little bit. And then z will be the number of people finishing third. Sorry about that. Okay, so we've got our variables defined, and now let's take a look at how we can come up with some equations. And I'm back to this point here, this first sentence, and I'll try to color code these. 24 total individuals placed. That means they came in either first, second, and third, or third. So I can, since I've got these variables that represent the number of people that finished in each of those places, my first equation is just going to be the sum of all those people. The first place finisher, second place, third place, totaled should be 24. All right, so that's my red equation. Okay, now this is another clue. They give you the total number of points, and they also give you how many points each place earns. So this blue equation, I'm going to highlight it here. The blue wording is going to represent or be represented by the blue equation. If I take 3 points times all of the people who finished first, that's 3x. 2 points for all of the people that finished second, that's 2y. 1 point for all the people that finished third, that's 1z. All of those points combined should add up to 53. Okay, so 2 equations down, 1 to go. And the final equation is going to be made up from this very last sentence. We'll do it in green. They tell us that there were as many first place finishers as second and third place combined. Okay, so just think of it this way. The first place finishers, which we have as x, should be the same as the second and the third added together. That's just another way of saying combined. So we have our system. This is a system in 3 variables. If you have 3 variables, then you have to have 3 equations. That's always true. And so now I want you to take it from here, and we've basically done letter A, but then I want you to find out the actual numbers of people that finished in each place. And if you, I'm going to let you pick. You can choose either substitution or elimination, but I hope you recognize that this sets up really well for substitution, because in this last equation, you already have x solved for, and so all you really have to do to get started is replace the x variable in the other two equations with y plus z. And then once you do that and you combine like terms, you've got two equations and two variables, and then if you want to, you can go to elimination. But I wanted to help you get it set up and then see if you can take it from there, and then see on your own if you can wrestle with and come up with the answer for the second word problem, which is number 19. So I hope that helps, and just let me know if you have any questions.